Hey everybody, Dr. A here, and in this video we're going to be exploring another example of using Mohr's circle to determine principal stresses and maximum shear stress. So let's go ahead and get started. In the given information, we're being asked to use a Mohr circle analysis to compute the principal stresses and maximum shear stress for the element. So let's take a look at the element we have here. We have this loaded element where we have a normal stress acting in the horizontal direction, and it's equal to 20 psi in compression. Notice on both sides here that represents 20 psi compressing in the horizontal direction. In the vertical direction, we have 60 psi causing tension. So we have this 60 psi causing tension on the top surface and the bottom surface. And then we have an applied shear stress acting on all four faces of the element, and that equals to 40 psi. Now we need to be careful of the sign convention here as we get started with our solution. So let's go ahead and gather up our information related to our solution. So sigma x is going to be negative 20 psi because that 20 psi acting on either vertical face is compressing the element in the horizontal direction. Then we have sigma y acting in tension on the two horizontal faces, and that's going to be equal to 60 psi. So that's positive because it's acting in tension. And then we're going to have tau xy, and that's going to be negative 40 psi. So if you're a little rusty on the sign convention of the stresses acting on an element, you can go back and rewatch one of my previous videos that provides background information on this topic. All right. So to determine the principal stresses and maximum shear stress using a Mohr circle analysis, we want to define 2 points on opposite sides of what will be the Mohr circle. So we're going to define a point A, and point A corresponds with a orientation angle of 0 degrees, and that's going to be sigma x comma tau xy, and that's going to give us negative 20 psi comma negative 40 psi. So that's going to be 1 point on the circle. Point B is going to be a point on the opposite side of the circle from point A, and that's going to correspond with an orientation angle of 90 degrees counterclockwise. And that's going to be defined by sigma y comma negative tau xy. And that will be 60 psi comma positive 40 psi because you have a negative tau xy, and tau xy is negative 40, so you have the negative times the negative gives you the positive 40 psi. So now that we have these two opposing points that are defining the diameter of the Mohr circle, we can go ahead and sketch it out. So I'm going to go ahead and sketch my, my axes here. Now I like to freehand sketch my axes because I think it's a little bit more natural when I teach and explain these things. But I would suggest you try to draw things a little bit to scale, maybe with a straight edge, so you keep things kind of organized in your notes as you write this information down, all right? So I'm going to go ahead and scale off my axes. I'm going to use 80 psi here, and that'll put this at about negative 80. And this will be about 80 up here. This will be about negative 80 here. And then we can scale off the half points here, 40, 60, 20, 40, 60, 20, and so on. Just like that. Okay. So now we've got our axes pretty much all labeled, and we can plot these 2 points. So point A, we're going to go negative 20 and negative 40. So point A is going to be about right here. And again, I'm freehanding this, but for you taking notes, I would maybe try to practice drawing this nice and neat. Point B is going to be positive 60 and positive 40. So that's going to put us about right here. So that'll be point B here. And this defines the diameter of the circle. So we can, put a line straight through here and give us that diameter. Now, if you draw this really nicely into scale on your paper, you'll find graphically that the center of the circle is right here at 20 psi. But if you want to calculate that and show that in calculation form, we can say that the center is equal to sigma average comma 0. And what is sigma average? Well, that's just going to be sigma x plus sigma y over 2. And so substituting in sigma x plus sigma y over 2, and again, that sigma x has a negative associated with it, negative 20 psi. So when you crank this through, you do get, in fact, 20 psi positive. Okay, so there's our center. All right. Now, what we can do from here is swing a circle through here. Now, again, I'm going to freehand this, so my students know very well that my freehand sketches are often not the most beautiful, but we're going to do our best here. So I'm going to swing this around, okay? And we're going to swing this down about here. Swing this out here. And we can maybe fill in the dashed lines a little bit. And like I said, I like doing this freehand even on the iPad just to kind of make it a little bit more organic. So let's go ahead and start figuring out aspects of this. Well, here's a radius, right? And remember, it's a circle, so it's got a constant radius. How do we get the radius of this circle? Well, here's what I can do. I can drop a vertical line down right here. Now, that vertical line that I just dropped down in green is going to be affiliated with that point B, all right? And when I drop this vertical line down, it's going to give me a right angle with the sigma axis. So what I can do is I can analyze this right triangle that I just formed here, all right? So what you can do is you can extract that right triangle and you can use the Pythagorean theorem to get this radius r, all right? Now, how do we do that? How do we know what the dimensions of this right triangle are? Well, the height of this right triangle is this dimension right here. Well, that's the vertical component of point B. So that's just 40 psi. That's quite literally, it's this 40 psi is that dimension, okay? What about this dimension line here? What about the base length of that right triangle? Well, if you just look at your axes, that's 60 psi minus this 20 psi gives you this distance, right? Because the 60 is measured from the origin. So you say this 60 psi minus this 20 psi, and you get this little green dimension line here. And of course, that is also 40 psi. So we can use the Pythagorean theorem to get that radius by saying 40 psi squared plus 40 psi squared, and then square rooting all of that. So the radius becomes 50, crank this through in your calculator, but I get 56.57 psi. Now, what do we ultimately need? We need the principal stresses and the maximum shear stress, right? So what are the principal stresses? Let's remind ourselves. Sigma 1 is the major principal stress, okay? And it is the point on the Mohr circle where the circle intersects the sigma axis, okay? So the circle itself intersects this horizontal sigma axis in two spots. Once here, and that's going to be the major principal stress, and then once over here, which is going to be the minor principal stress. So I can put these 2 points here, and this point here is going to be sigma 1, and this point here is going to be sigma 2. So sigma 2 is what we call the minor principal stress. All right, so what are these values? Well, all we need to do is say, hey, I know what the center is. I'm going to take that center value, which was sigma average 20 psi, and add to it the radius, okay? How do I know to do that? Well, remember, the radius is what it is, right? The radius is the distance from the center of the circle to the edge of the circle all the way around. So this distance right here is also the radius, okay? So I can write this as sigma average plus the radius, which I have both of those values, right? It's 20 psi plus 56.57 psi. So that gives me 76.57 psi. Now, what about the minor principal stress? Well, that's where the circle intersects the sigma axis on the opposite side over here. Well, I do a similar process. I start from the center, and I say, okay, it's the center value, but this time I'm going to subtract the radius to take me to this edge of the circle over here, all right? So that's going to be sigma average minus r, and that will give me negative 36.57 psi. So these are parts of my answer. Now remember, numerically speaking, the major principal stress is the bigger of the two, okay? So how do you know which one is major and which one is minor? Well, again, the major principal stress is the larger of these two values, okay? It's the numerical larger of the two values, all right? Now, what about the last thing the problem asked for? It asked for the maximum shear stress. So the maximum shear stress occurs at the very top of the circle, so right about here, okay, right about here. Now, if you drew this to scale, then this would look a lot nicer than it does, okay? So what is that distance? Well, that's still the radius r. So r is tau max, which is 56.57 psi. All right, so those are your three answers. Now, here's what I want you to be careful about when you're sketching this on your own, okay? If you sketch this really nicely to scale, it's going to be a nearly perfect circle, okay? Theoretically, it'll be a perfect circle. Now, if you notice, the radius and tau max is 56.57. Now the way I drew this looks like it's above 60, okay? That's because I freehanded it. I didn't draw it very nicely, okay? If I were to redraw this really nice and neat, I might, recreate this curvature a little bit. And, if I recreate this curvature a little bit more to scale, then, the 60 would be maybe right here, and then here is that tau max, okay? So again, this kind of illustrates the importance of trying to draw your axes when you're freehanding this. Use a straight edge and try to draw things to scale so everything is proportional with each other. And then what you end up sketching graphically will match what you are calculating analytically using Pythagorean theorem and the geometry principles, okay? So if you found this helpful, please hit like and subscribe and be on the lookout for other content similar to this. Thanks for watching.